Welcome to the Deep Dive, where we plunge into your source material to extract the most important nuggets of knowledge and insight. Today, we're dissecting the very latest in longevity research, really hot off the presses from just this past week.
That's right. We're looking at some cutting-edge papers, proposing new mechanisms, new targets for extending human lifespan and health span.
And it's a mix, right? Some peer-reviewed, some not yet.
Exactly. Some are published, others are fresh preprints on platforms like bioRockSev, that's pronounced bioarchive. So, they're exciting, definitely, but still waiting for that critical peer review.
Okay.
So we'll approach them with, a really curious mindset, but also a rigorous and skeptical one, trying to figure out what might actually be impactful for, future biotech development.
Sounds good. So if you're ready to get quickly and thoroughly informed on the science of living longer and maybe healthier, let's unpack this. For years, there's been this kind of fundamental dilemma in longevity research, hasn't there? This question of trade-offs.
Oh, absolutely. Does extending life inevitably mean you sacrifice something else, like fertility or growth or stress resistance?
Right. Well, this week, we've got a couple of papers that offer some maybe tantalizing clues that we might be starting to see ways around that compromise. First up, there's a paper reporting a truly, dramatic finding in the common fruit fly, Drosophila. It's titled, "The Mediator Complex Subunit Med19 Extends Healthy Lifespan in Drosophila by Preventing Cellular and Organismal Frailty."
Okay.
This one's from the Restore Research Center, just hit by ORXFA on June 18th, 2025. Authors include Payet, Guillou, and Bernat Fabre.
Yeah, and what's really striking here, and I think demands both excitement and, a healthy dose of skepticism, is just the sheer magnitude of the effect they're reporting.
How big are we talking?
They're saying upregulating a single gene, this Med19, extended the median lifespan in these flies by nearly 90%.
Oh, really?
90%.
Yeah.
And maximum lifespan by 51%. I mean, this is an enormous gain in a model organism. The paper argues that Med19 acts as a kind of master transcriptional regulator, and it delays what they're calling the frailty point, that age where mortality rates just shoot up in a population.
And that emphasis on health span, not just lifespan, seems really key here. How exactly did they measure the healthy part in the flies? What improved?
That's a great question. It wasn't just about survival time. The flies also showed significant improvements in physical function, things like better climbing ability, which is a standard assay.
Right.
And they had enhanced resistance to common stresses like oxidative damage, genotoxic challenges. Even more interesting, maybe, is that they found Med19 levels naturally go down with age.
Ah, okay.
And when they restored Med19 levels in older flies that were already sort of frail, it didn't just slow things down, it significantly increased the remaining lifespan and pushed back frailty even further.
So that hints at rejuvenation almost, not just prevention.
Exactly. It hints at potential for rejuvenation, not just slowing aging from the start, but, that magnitude, nearly 90% median lifespan from one gene. It's truly exceptional. It rivals some of the biggest effects ever seen.
Which brings us back to the skepticism. It's a bioRx paper, unreviewed.
Precisely. Independent replication is absolutely essential here. And while it's incredibly promising, you always have to remember lifespan extensions in flies, they often don't translate directly to humans in the same proportion. Not even close sometimes.
Yeah, good point. We've seen that before.
Think about things like the DF9 gene in C. elegans worms years ago, even bigger extensions there. So, got to keep the context.
So given that necessary skepticism, what experiments really need to happen next to feel more confident about this Med19 finding?
Okay, first off, independent replication. Different labs, different Drosophila strains, just to make sure it's not some weird artifact of one specific setup.
Makes sense.
Then, you'd really want to see a mouse model, an inducible Med19 upregulation so you can turn it on when you want. And you'd have to watch very carefully for any signs of cancer, given Med19's role in basic gene transcription.
Right, that's a big risk with anything controlling transcription so broadly.
Sure. Then maybe tissue-specific studies. Is it working everywhere, or is one organ key? And finally, a really deep dive, proteomics, metabolomics, to figure out what pathways Med19 is actually tweaking downstream.
Okay, so Med19 offers maybe one glimpse into this idea of cost-free longevity. But building on that theme, another paper this week tackles an even more sort of classic trade-off.
Ah, the insulin signaling pathway.
Exactly. The long-held link between extending life via insulin signaling changes and nasty side effects like insulin resistance. They might have cracked it.
Okay, I'm intrigued.
This paper is in PLS Genetics, published June 16, 2025. Title: An insulin-sensitive Drosophila insulin-like receptor mutant remodels methionine metabolism to extend lifespan. Authors are Mark Tatar, Wenjing Zhang, Shweta Yadav, and the team at Brown.
Right, this study is, I have to say, exceptionally elegant. It really addresses a hurdle we've had in the field for decades.
Which is?
Well, we've known forever that dampening the insulin IGF-1 signaling pathway, ISMS, extends lifespan in many species. But it almost always comes with these trade-offs. You get insulin resistance, the animals are often smaller, fertility tanks.
The costs we were talking about?
Exactly, the costs. This paper identifies a specific mutation, just a single amino acid change, Dinin R353, in the fly insulin-like receptor that seems to uncouple these effects.
Uncouple. So they got the long life without the downsides. That sounds, well, like a game changer if it's real.
Pretty much, yeah. The mutant flies showed robust longevity extension, but they stayed insulin sensitive, they were full-sized, and they were highly fecund, meaning fertile.
Wow.
That's a really significant departure from the standard isomutants.
And how did they do it?
It seems they remodeled methionine metabolism.
Right.
Actually, they got the benefits of the thionine restriction, another known longevity intervention, without actually changing the diet.
So it's like a genetic mimic of dietary restriction, specifically methionine restriction, mediated through the insulin receptor.
That seems to be the idea. And it provides a potentially much more refined way to intervene. Instead of just broadly inhibiting the receptor, maybe you could develop drugs that specifically target one part of it. They point to the kinase insert domain to nudge it into this beneficial state.
That's fascinating.
It really makes you ask, can we get the benefits of hitting these core longevity pathways without paying the usual price? This paper screams yes, at least, in flies.
If this uncoupling holds up and translates, what are the next steps to push this towards something useful, potentially even for humans?
Okay, technologically, cryo-EM would be amazing. That's electron microscopy at super cold temperatures.
Yeah.
It lets you see the actual 3D structure.
To see how the receptor shape changes.
Exactly. See how this mutation changes the shape and causes the uncoupling. Then, critically, engineer the equivalent mutation in mice. Does the uncoupling work in mammals? That's the million-dollar question. And from a biotech perspective, you'd want high-throughput screens. Look for small molecules, potential drugs, that specifically bind to that kinase insert domain and mimic the mutation's effect.
Finding a drug that does what the gene tweak does.
Precisely. And finally, some detailed genetic work epistasis experiments to see exactly how this mutation interacts with the known methionine restriction pathways. Really nail down the mechanism.
Okay, we've looked at some pretty specific genetic and molecular tweaks. Now for something, well, unexpected. A psychedelic compound entering the longevity chat.
Uh-oh, where are we going with this?
This paper is titled Lysergic Acid Diethylamide Extends Lifespan in Kinnerhabditis elegans.
LSD in worms.
Seriously. Published on bioRxiv, again, June 16th, 2025. Authors Carrillo, Silva, Sanana, and colleagues from the Dior Institute in Brazil.
Okay, well, that's certainly novel. What's the proposed mechanism? How could LSD possibly extend worm lifespan?
What's fascinating is the idea that LSD, which we know mainly acts on serotonin receptors, seems to mimic caloric restriction in these worms.
How so?
It reduced their lipid stores, seemed to reduce overall protein synthesis, and it activated a key transcription factor called PHA4FXA, which is known to be involved in CR response in worms. Right, PHA4FXA is a known player.
Crucially, it did all this without the worms actually eating less. So it looks like a true caloric restriction mimetic, something the field has been hunting for ages.
A drug that gives CR benefits without the restriction part, but it's LSD. What are the implications here? It seems like a massive hurdle for translation.
Well, yeah, the psychedelic properties obviously make direct human use as a longevity drug.
Yeah.
Challenging, to say the least. Probably a non-starter with LSD itself.
Right.
But it forces us to think differently. It opens up a whole new chemical space. Could other non-psychedelic compounds that modulate serotonin signaling have similar effects? Maybe derivatives of LSD that lack the psychedelic activity but keep the metabolic effects.
That's the key question then, isn't it? Can you separate the longevity effect from the psychedelic effect?
Exactly. And also, how conserved is this link between serotonin signaling and these core metabolic CR-like effects across species? That's a big unknown.
So next steps for this rather surprising finding.
Definitely need detailed genetic work in the worms. Confirm that it really depends on known longevity genes like DAF16 and FAE4. That's standard epistasis analysis.
Okay.
And crucially, test non-psychoactive serotonergic compounds. See if you can find something that gives the lifespan benefit without the trip. Then check for conservation. Does it work in flies? Does it work in mice? Though mouse studies with LSD obviously have their own set of regulatory and practical hurdles.
Yeah, I can imagine. Okay, switching gears pretty dramatically now, away from whole organisms and drugs, down to a really fundamental cellular mechanism.
Okay.
We have a paper titled Reversible Proliferative Arrest Induced by Rapid Depletion of RNase MRP, published in Cell Proliferation, June 19th, 2025, from Yuan Liu, Xiang He, Kawan Piero, and their team at UC Riverside.
RNase MRP. Okay, so this is getting into the nuts and bolts of cell function, ribosome biogenesis, right?
Exactly. Making ribosomes, the cell's protein factories, what they found, and this is directly in human cells, is highly novel.
Go on.
They showed that if you rapidly deplete this enzyme, RNase MRP, you can push cells into a long-term state where they stop dividing. Proliferative arrest. But, and this is the crucial part, it's reversible.
Reversible.
The cells stayed viable, just quiescent, for weeks. Then, when they restored RNase MRP levels, the cells fully resumed dividing as normal.
Wow. So it's like hitting pause on the cell cycle, then play again. Kind of a suspended animation for cells?
You could definitely think of it that way, yeah. It really reinforces this idea we see in other longevity interventions like caloric restriction or drugs like rapamycin, that dialing down biosynthesis, slowing down the building processes, can promote cellular stability and maybe longevity.
Makes sense.
Now, translating this into extending the lifespan of a whole organism by putting all its cells on pause, that's a huge leap, a formidable challenge.
Right. Sounds like science fiction almost. It does. But it gives us a powerful new tool and a very specific target, RNase MRP, for manipulating these cellular states. It really makes you wonder, could temporarily slowing down life at the cellular level be a path to extending it overall, or maybe for other applications?
Like what? Organ preservation.
Exactly. That's a huge potential application. Imagine keeping organs viable for much longer outside the body before transplantation. That would be transformative.
So what experiments are needed to explore this further?
Well, the obvious big one is a mouse model. Can you create a mouse where you can inducibly knock down RNase MRP, maybe systemically or in specific tissues? Can you achieve this quiescent state in vivo and, importantly, reverse it safely?
That sounds tricky.
Very. Then definitely explore the organ preservation angle ex vivo. And on the basic science side, use single-cell multiomics, look at all the genes, proteins, metabolites in these arrested cells to really map out what this quiescent state looks like and how it compares to other known dormant states like cellular senescence or diapause.
Okay, one final paper to cover. This one sounds very promising, targeting mitochondria directly, but it's just an abstract for now.
Yeah, it's a bit of a teaser, this one. Published in JCS, the Journal of the American Chemical Society, on June 13th, 2025. From Kyushu University in Japan, Arnada, Kawahara, Shimada, and others.
And the title.
A nucleic acid prodrug that activates mitochondrial respiration, promotes stress resilience, and prolongs lifespan.
Okay, hitting all the buzzwords there. Mitochondrial dysfunction is a core hallmark of aging, right?
Absolutely. So this paper describes a novel nucleic acid prodrug. The idea is it gets into cells and boosts levels of things like ATP, the cell's energy currency, presumably by improving mitochondrial function.
And what does the abstract claim it does?
It reports that this prodrug activates AMPK. That's a key energy sensor involved in longevity. It enhances fatty acid oxidation, so burning fat for energy, boosts stress resistance, and the big claim, it markedly extended the lifespan in a test organism.
Sounds fantastic, but you said it's just an abstract. What are the catches?
Well, the abstract is, frankly, frustratingly incomplete. It completely fails to mention the specific model organism they used. There's worms, flies, something else. And critically, it doesn't give the actual effect size. How much lifespan extension are we talking about? Markedly doesn't cut it scientifically.
Yeah, those are pretty crucial details to leave out.
Absolutely. Plus, you have to be cautious. Just broadly boosting cellular energy isn't always good. It could potentially fuel unwanted growth, like cancer cells. So safety, long-term toxicity, those are going to be huge questions for any human application.
Right, so it raises the question, can you get these energy benefits safely without those dangerous side effects?
That's the key question for the biotech angle, definitely. Can we achieve this without the potential downsides, especially the cancer risk?
So what needs to happen next with this one?
First, we desperately need the full paper. Get those missing details, the organism, the actual numbers.
Hmm.
Assuming the results are solid in whatever model they use, likely worms or flies, given its JZACS, and probably focused on the chemistry first. Then the next step is comprehensive mouse testing. Toxicology, pharmacokinetics, how the drug gets absorbed, distributed, metabolized, excreted. And critically, test it when given later in life. Does it work in middle-aged or older animals? That's the real test for an anti-aging intervention.
Okay, wow. We've journeyed through quite a bit there. Single gene tweaks in flies, uncoupling insulin signaling, LSD in worms, pausing cells, boosting mitochondria. Quite a week. As we step back and look at all these together, what are the bigger themes? What's the grander story emerging for you?
Well, if you connect the dots, almost all these interventions, maybe except the RNase MRP one, which is more about quiescence, they ultimately circle back to modulating core nutrient sensing and metabolic pathways.
Right, metabolism seems central.
It really reinforces how inextricably linked metabolism and aging are. But maybe the most profound takeaway, especially for you listeners in biotech, is this emerging distinction between what we were calling costly and cost-free longevity.
Costly versus cost-free. Can you expand on that framing again?
Sure, think about traditional interventions, like the LSD study, which mimicked caloric restriction, or the classic insulin receptor mutants we talked about. They often extend lifespan, sure, but there's a price. Reduced fertility, smaller size, maybe immune issues. That's the costly approach. It fits with this old idea of antagonistic pleiotropy genes, good early in life, become bad later.
Okay, the trade-offs.
Exactly. But then you look at the Med-19 paper, or especially that in-error 353 insulin receptor mutant paper. They offer this tantalizing glimpse of a cost-free paradigm. They report dramatic lifespan extension while actually preserving or even enhancing things like vitality and fecundity in the flies.
That seems to challenge the old assumptions.
It really does. It suggests that maybe those trade-offs we thought were inevitable laws of aging aren't absolute. Maybe they're context-dependent outcomes that you can actually subvert if you modulate the pathways precisely enough.
Which leads to a big question for our listeners, right?
Absolutely. It raises this crucial question for you, and really for the whole future of biotech.
Yeah.
If we can achieve longevity without the traditional costs, what does that really mean for the future of human health? How does that change the game for developing anti-aging therapeutics? So overall, the impact of this week's papers for longevity biotech, I think, is pretty significant. They provide new targets like Med-19 or that specific domain in the insulin receptor, and new blueprints for designing interventions that might avoid old limitations.
But with the usual caveats.
Always. You have to remember, the truly world-changing papers, the ones that fundamentally shift the field, like maybe some we saw earlier this year, those are rare. These papers are exciting, they open new doors, definitely, but the huge gains we see in flies and worms often shrink dramatically by the time you get to mammals, let alone humans.
So crucial steps, building understanding, but the path to human application is still long.
Long and complex, exactly.
Well, what a fascinating deep dive into the absolute cutting edge. From uncoupling core pathways to surprising psychedelic links, and even pausing life at the cellular level, it really feels like our picture of healthy aging is becoming much more plastic, more nuanced than maybe we thought.
Absolutely. I think the real shift we're seeing is towards understanding how to precisely modulate these pathways, getting away from just blunt inhibition and towards achieving optimal health and longevity outcomes. It pushes us to think about how we might reactivate resilience that's maybe latent, even in older individuals.
So perhaps a final thought for everyone listening today as you reflect on what we've discussed. If the biology of aging really is this malleable, this tweakable, how might our fundamental understanding of human health and even our very definition of old age change in the decades to come? That's it for this edition of The Deep Dive. Thank you so much for joining us, and we look forward to exploring more fascinating topics with you next time.